I forgot to bring my extra, analog glasses, so it's going to be a little bit difficult for me to see my own screen because that's just the wrong distance for me. All right, so what we'll do today is I'm going to give you the solution of the 3x3 carry local head adder. Many of you have done it already, okay? But I'm going to do it, and I'm going to do it in a way where I'm combining both an adder and a subtractor in one single design, okay? So we'll go ahead and take a look at, this is a perfect opportunity for us to review some of the material that we have talked about so far. Specifically, we'll talk about 3x3, not 3x3, but binary addition, binary subtraction. And if we have time, we might even build in the circuit to deal with the sign flag, the overflow flag, and the L flag that we talked about right before I got sick. Is that okay? So kind of look at this as a demonstration in LogicSim. Most of you got to use you know how to use LogicSim already, but it will also be a good review session on the topics, the concepts that we have been talking about, except now it's implemented as logic. So what I'll do is I'm going to bring up the notes on binary addition, which is right here, because I know that I cannot remember the equation, so I'm going to have to look it up. And most of the things are in section 6, so we'll skip all the way to section 6 for now. And then we'll go ahead and start. This is the part where it gets kind of difficult because I can't see my own screen. Go. All right, so here's LogicSim, and then we'll start with the basic design. We have, let me look up the assignment first, because I want to make this look exactly like the one that you guys had to do. So I'm going to look up the homework assignment and figure out how the ports are supposed to look like. And by the way, thank you for those of you who, thanks to all of you who reported the problem of, when you have an answer of 0 and you try to submit the test, it will tell you that those questions are missing or the answer to those questions are missing. So I have reported that to the campus distance education people already, and then we'll see how long it takes, for Canvas to actually fix those problems. I'm suspecting half a day would be more than enough. All right, so here's X, which is a 3-bit thing. And then I duplicate it so that we now have Y, which is also a 3-bit thing. And you can see how I use the top bar here for my input pins, because those input pins automatically have 3 states turned off. And some of you may notice, when you do not do it this way and you pull the input pins from wiring, it would have X, in it, okay, because you have a 3-state turned on. So this is the reason why I always pull the input and output pins from the top rather than from the side. The last one is K0. There we go. And then we want to create the tunnels that we have to deal with. So the tunnels that we have to deal with, or in your homework assignment that you have to deal with, specifically are the P, and then the Q, well, G and Q. I cannot remember how they're ordered, so we'll change the way they are ordered, in just a little bit. So this one, P, G, and Q. There we go. All right, so since you have answered that question already, the main purpose of tunnels is so that we can have logical connections between points on the same design in LogicSim. So tunnels of exactly the same name are basically electrically connected, and that is the reason why we have tunnels. They do not serve the same purpose as pins. So pins tunnels, and probes are different things in logic sim. Let me just kind of point that out to you, where you can find all of those things. So we got pins here, we got a tunnel here, and we got a probe here. They're right next to each other in logic sim. What a pin is basically the same thing as a parameter in a function in C and C++ programming. In other words, a pin is what allows outside signals to go into a circuit, and it is also what allows the output of a circuit to become available to something that's outside of the circuit. If you were to hold on to an actual chip, okay, an actual IC integrated circuit, pins would actually correspond to the actual pins on the circuit, contact points. Yep.
I think somebody asked this before, and I don't remember. Each bit inside of, like, if you have a 3-bit number, each one of those have, like, their own pathway?
That is correct. So in an actual circuit, each individual bit of a pin has its own contact point, so that when you solder that onto a motherboard, onto a circuit board, each one will have its own unique pin, unique conductor. Because you cannot combine multiple bits into a single conductor in a real circuit.
I was wondering if maybe it was like a time-based thing, but...
Nope. Well, unless you have some really kind of fancy thing that can multiplex, based on timing. But most of the time, no, that is not true. All right, so this is also a neat trick here. Let me show you what I'm doing here. I look at all three and I say I want to change all three to 3 bits. So when you multi-select items, and it will basically allow you to change certain things that are applicable to all of the selected items. So it's kind of a neat thing to do, because you can just kind of shift click or control click on multiple things and change all of them at the same time. So now all my tunnels are 3-bit wide. Okay. I can also create 3 more. Okay. For all the input pins, which is also what you saw in your homework assignment. So I'm going to put those over here and change the facing. So I can change all of them to face east, like so. But now I have to go back and change these to individual ones. So I would call this one X, and call this one Y, and then call this one K0. And K0 is only 1 bit. So it also needs to have the other change to change the number of data bits back to 1. There we go. So pretty mundane stuff that I'm doing at this point. And then we need to make a copy of this. Put it back here because I had those tunnels arranged like this earlier. And then flip these back to face the other side. So I'm just resetting up the whole thing so that it looks kind of like your homework assignment. The name of a pin and the name of a tunnel, they can be different or they can be the same or different. It doesn't really matter. There's no logical relationship between a pin and a tunnel of exactly the same name. Only tunnels of the same name are related. Are there any questions about all of these concepts? So we have a width issue because I apparently did not change that one or changed it in the wrong way. So this one is supposed to be 1 bit, and then this one is supposed to be 1 bit as well. There we go. All right. So does that kind of resemble your homework assignment? Okay. So the next thing we need to do is to figure out, okay, from the X, Y, and K0, how do we come up with P and G and Q? Okay. So I will work with Q first because that is what we talked about in the notes first. So we'll deal with the Q first. So we go back to the notes, okay, go back to the module, and the Q is defined before section 6. So you can, the great thing of using a spreadsheet, or not a spreadsheet, but using HTML, as a display here, is you can use on the browser, you can search within the page, and then you can just type Q and then open bracket. That will automatically help you locate certain things that are useful. So Q of I is basically by definition the result of adding xi and yi. And that is not even binary, okay? So this part of the discussion does not even bring in binary numbers. It's just the result of adding 2 digits, but with carry out of the consideration. So it's not including the carry part of this. So then you look down a little bit. The next section talks about binary number. So if you look into section 5, it talks about how R is implemented. So right here it says RXY is implemented in binary as oh, you cannot see it, can you? Okay, you can see it, but it's not highlighted because I moved my mouse pointer. Okay, so there we go. So if X and Y are binary, meaning they're only zeros and ones, then the result of adding X and Y can be done using only logic operations, which is X and not Y, or not X and Y. Is that part okay? And then very obscurely, somewhere in here, there's also a mentioning of exclusive OR. So I obviously cannot remember exactly where I put it, so I'm going to search for that. There we go, right above that. So there's a Boolean operator called exclusive OR that can do this, but we can also spell it out using just regular OR and regular AND and regular NOT. Is that part okay? So that means the Q is basically the exclusive OR between the X and the Y. The question is, can we use a multi-bit gate to do it? To answer that question, you have to basically ask the question, is Q0 computable by X0 exclusive OR Y0? Is Q1 the result of X1 exclusive OR with Y1, and so on? So if the answer is yes to all 3 bits, bit 0, bit 1, and bit 2, then you can use a multi-bit gate. So in this case, the answer is in fact yes, because if you look at the equation, it applies to every single bit position. So in LogicSim, the way we do it now is we go to gates, we pick out the exclusive OR gate, okay? Now in the homework assignment, the gate is already picked out. So if you're not familiar with the shape of the exclusive OR gate, you can look it up, in the gates tab over here, and find that it is actually exclusive OR. So once we have the exclusive OR gate, we have to change the bit width to 3, change the number of input to 2, and I personally like a smaller gate when I don't need to have all the different pins. So that becomes my Q. And so when you see a red wire, you have to basically ask, okay, what is the red wire representing? A red wire is always representing something that needs to be fixed. So are orange wires. A red wire appears when the output of a gate is used, but we have not defined what is going into the gate. So the input pins of this gate is not specified, but the output pin is now connected to somewhere. So it doesn't seem to make sense, because how do I know the output if I don't know what the input is? So that's why it is red. So now we just know that, okay, we need X to go into one of these, and Y to go into the other part, like so. So now we got Q done. Are we good so far? Okay. Next one, the next two, okay, because these two are closely related, will be the P and the G pins. So these two are defined in section 6 in once again a kind of obscure portion of it. It is a very important concept, but it is defined at a very kind of obscure portion, which is right here. So this is defining G of I, which is I is the bit number. So bit I of G is the end of bit I of X, bit Y of Y. So now the question is, can I use a multi-bit gate to do this? What do you think? Why do you think it can use a multi-bit gate? Because bit 0, yeah, go ahead.
Oh, all here. Okay, never mind, sorry.
All right?
I got kind of lost, sorry.
That's all right, no problem. Anyone else? Why can't we use a multi-bit gate in this case? Because we are performing the same operation for each bit position. So G0 is X0 and Y0, G1 is X1 and Y1, and then G2 is X1 and Y2. So that's why we can use a multi-bit gate. Okay? So we go back to LogicSim, go to an AND gate, and once again we change the bit width to 3, and then we change the number of inputs to 2, and then we change the appearance to narrow. And this one's for G. Okay, like so. And then we just use X again to hook up to one end of the AND gate, and then use Y to hook up to the other end of the AND gate. When we're dealing with an adder, it doesn't really matter which port you're connecting it to, because it is symmetric. Because we're doing the same thing to both the X and the Y, so it doesn't really matter which end. So with the only one left is P. So when you look up the notes here, it defines right here, not right here, this part here. So it says, PI is XI or YI. So once again, we can use a multi-bit gate to do this, because P0 is X0 or Y0, P1 is X1 or Y1, and then P2 is X2 or Y2. So you can see how we are performing the same operation to all the different bit positions. That is the reason why we can use a multi-bit gate. So that, it's a shorthand, okay? There's no such thing, as a hardware device as a multi-bit gate, but it does make it easier to look at in terms of the design. So we go back here, we pull out an OR gate, we do the same thing. We change the number of bits to 3, number of inputs to 2, and change the shape so it's a little bit smaller. There we go. Oh. There we go. Are there any questions about the differentiation between the number of input pins as opposed to the number of bits or the bit width of a gate? Because those two concepts are entirely different, even though they may seem related. Are there any questions regarding those? No questions? Okay, all right. All right, so we got the P, the G, and the Q done in this case. And there's not much I can do further than this until I have all the K bits done. So now we need to compute the carry bits. So now we go back to the notes here, and we look up the carry bits. So the first one we need to look at is K1, or some people start with K2 or K3, which is actually not a bad idea. So we'll start with K3. We'll get the most difficult one out of the way. Then the easier ones would actually be very easy to deal with. All right, so we look at K3, and you'll go like, K3 has 3 rows of equations. Which one am I supposed to use? What do you think? The last one, right? Why do we use the last one but not the first one? The first one looks so much simpler. Yes?
Because then we have 3 layers, and we don't have so much coming out of it.
Okay.
4 layers on top of it.
If you just look at it like this, the first row, which defines K3 to be G2 plus or P2 and K2, that's only 2 levels of gates also. But there's a problem with that definition. Yes? You have to solve for K2. In other words, the dependency of K3 on K2 is still there on the first row, on the first line. Okay? And that defeats the entire purpose of carry look ahead. Is that okay? Yes, go ahead.
But can we use the second?
Okay, so let's take a look at the second row. If you use the second row, then you still have more levels of logic than necessary. Because if you look at the second row, then we have one level of gate logic to do this, one level to do this, one level to do this, then one level to do this, and then one level to do this. So we still have more levels of gate logic than the third row. So we still don't want the second row, we want the last row. So, okay, can I answer your question back there?
Are you streaming this?
Huh?
Are you streaming?
I certainly hope so. Yep, I'm streaming. It's good to ask. Yep. So getting back to the notes here. So what we want is the last row. I mean, the general idea is if the last row is not needed, why do I spend the time to derive it? So that's one clue that we want the last row. And then the second one is even more important because the whole idea of carry look ahead is we want the adder to spend exactly the same amount of time regardless of how many bits is in the adder. Okay? If we use the first row, then it's going to take more time because now in order to compute K3, we need to know K2 first. In order to compute K2, we need to know K1 first, and then K1 itself can be computed because it only relies on K0. But that means we have propagational delay. We have additional propagational delay. If you look at the last row, we need one AND gate to do this, one AND gate to do this, one AND gate to do this, and then one OR gate to take all the outputs of the AND gates and perform that one calculation. So not counting the propagational delay to get the P and the G terms, because those have to be done anyway, we only need 2 additional gate delays. Well, but what about bit 64 in a huge, gigantic 64-bit adder? Well, then the AND gates will be very big. The OR gate is going to be very big. But in terms of level of gates, you only have 2, just like this one, just like K2, just like K1. You only have 2 levels of gate. That is the key. Is that okay? So I'm going to switch back and forth a little bit here so it can be a little bit confusing. So right here, I can now design, go to project and add a circuit. Yes, go ahead.
So in general, expanding the equation, does that reduce the amount of propagational delay that you would have? So like if you model it after the most expanded form of an equation, would that reduce propagational delay just in general?
If you expand,
if you model your circuit after the most expanded version
Uh-huh.
of an equation.
nope. I will show you because this is exactly the way I'm doing it, so I can show you how it's actually not going to increase the number of delay. Okay. All right. So we'll take a look at this, and I most likely forget what I just saw. So we'll add circuit, and I'll deal with K3 first. So we'll take the most difficult one and get it out of the way first. So I'm designing K3. The first thing we want to know is if you want to make a new circuit, do not assume that tunnels connect between circuits. They do not. So tunnels are more like local variables. So each one is local to the circuit where they are defined. Now, does it mean that we cannot redefine a tunnel called P and G and Q over here? Nope, you can define a tunnel all you want of exactly the same name, except the tunnel P, G, and Q on this particular logic design does not connect to those tunnels in main at all because they're local. They're like local variables. So that's why when you design the subcircuit, the first thing you need to think about are the parameters. In other words, from the outside of the circuit, what am I bringing in? Those are the pins, okay? So we got 2 pins, we got 3 input pins, okay? Okay. The first two are X and Y. So excuse me, I take it back. It's P, G, and then K0. And then the first two are also supposed to be 3 bit wide. I'll fix that later. Like so. And then I also know what is the output of this entire circuit. It is K3, which is a single bit. That's all I know. Is that okay so far? So now I need to go into the design and then figure out, okay, what am I going to do with this? Well, we need a big OR gate. So how many inputs do I need for the OR gate? That is the last operation. We got 4 inputs. This is 1, 2, 3, 4 inputs into the final OR gate. Okay, I'll deal with that first. So I will deal with the OR gate. That's gates. And this one comes close. It has 5, but I just need 4. So there we go. We have a 4 input OR gate and hook it up to K3. And it's going to give me an error right away because I have not specified what goes into this, which is fine. I'll deal with that later. So I switch back to my equation and go like, all right, we'll do the easiest one first, which is the first term. The first term is just G2. Okay, so we'll try to extract G2. Except we don't have G2 here. We have G, which is a 3-bit pin, and I only need bit 2 for this particular connection. How do I do that? What component do I need? We need a splitter. Very good. So we pull a splitter out, and we have several controls over here. The first thing we want to do is to make sure that we have a bit width of 3, which means there are 3 wires that we are dealing with. And we also want the fan out to be 3 as well in this case, because we actually need all 3 of the G bits. How do we know that? Because we can see right here, G2 is by itself needed as a single bit, G1 is needed for the second term, and then G0 is needed for the third term. So I need to split the input pin into 3 individual wires anyway. So I might as well just start right here and use a 3-bit splitter. Someone also pointed out to me that with a splitter you can have you can control the phasing appearance. Huh. Okay, I thought I saw that from somebody's design, but I couldn't find it here.
What are you trying to do?
To make the input centered.
Oh, appearance center. Appearance, the control.
Oh, it has centered here. Oh, okay, gotcha. Which makes it it saves a little bit of space. And then, looks like a trident.
And the wires are blue?
The wires are always blue when they're single bit and they're not determined.
But it's a trident. Like water?
Yeah. Oh, okay. Like deep water. Okay. Okay. So we'll split G to these 3 individual bits, and we know that bit 2 goes straight to one of the input pins. So we'll just pick this one here. Is that okay? So now we go back to the design because I cannot really remember all the components. So we now need a second gate, which is an AND gate, to compute the AND between P2 and G1. So we need, huh?
Do you want me to write it on the board?
Nah, it's okay. Unless somebody is getting dizzy. Because I actually have enough room to show it on the other side on my screen. So P2 and G1, we need an AND gate. So we need an AND gate here. And this one only needs 2 input pins. So we'll limit it to exactly 2 input pins. And someone actually had the great idea of labeling these things. So it is actually reflecting what the equation is. So I think that's a great idea, okay, to use the gate itself to self-document. So this one needs to go to this pin here. So we'll pick up P2, which is here, and G1, which coincidentally just goes straight across to this pin here, which also coincidentally just goes straight across. Trust me, I did not plan for this. I'm not like Professor Antos. He's a super planner. He's a super planner. I was evaluating his classes once, and he was able to write down on the whiteboard at the beginning of the class at what minute he'll be talking about which topic. And I was thinking in my head, I was just laughing my head off. It's like, yeah, right. Except he actually did it. He was able to plan his class down to the minute from the beginning of the whole class. Exactly. Apparently so.
You're trying to acquire P2 G1, but you got G2 in there.
I got, oh yeah. Nope, I got it right.
You got it right?
Yeah, this is P2, so P2 is not wired up yet. So I need,
Okay.
yeah, there we go. Okay. So the next one up is P2, P1, G0. Okay, so we will take another input, AND gate here. This time we got 3 input pins. And we'll still need a smaller design. And we'll just stick it here, where the output goes straight here. And this one requires, okay, that's not going to work out. I'm just looking at this and thinking, I can't make this look pretty anymore.
Use tunnels.
I could use tunnels, yes. So we know that G0 goes into the last input pin. So and for those of you who really enjoy this portion of the experience, you might make a good circuit board designer. Okay, so let me see, did I miss something? G0, and then we got P1 and P2. So we got G0, and then we got P1, but not P2. So we'll tap here for P2. Not the best looking design, but it will be functionally correct. There we go. All right, so we got one last one left, which is the larger one. So the last one we need to deal with is K0 and then all the P's together, okay? All right, so K0 is down here, and then we need to combine all of the P pins together. Okay, so we need an AND gate again, change the number of inputs to 4, and we'll still go for a narrower design, and we'll stick it up here. Okay, doesn't like that. I cannot make the design bigger. So now I have to move all of this stuff down a little bit. There we go. Yep, this one's not going to look nice, because I'm going to sneak in from here to connect to K0. And then all of the P pins are already connected here somewhere, so I can just tap it. There we go. Here's one. And, well, I don't really care about how this looks, so I can make it ugly. Okay. There we go. And the output goes into the last bin here. There we go. Oh, finally. So we got K3. Are we good so far? So I did not follow through my plan. In other words, I did not actually write down, what these, sub-equations are. So if you want to do that, you can kind of do it yourself, okay? Basically, look up, what this one is supposed to be. P2P1G0. So you can just document it here. P2P1G0. It's a great way to double check your design because, by looking at the equation, which now becomes the label of the gate, you can now check the input and see whether it is correct or not. So I personally think that's a great way to kind of double check your design and make sure that everything works. So I'm not going to spend too much time to self-document the circuit. Instead, I'll turn it into a component by looking at the design. So it looks like this. Some people say, I don't need to label the pins. I can remember it's P, G, and K0 in the input end, and there's only one output, which is K3. But, it doesn't take much time to label it. So I personally prefer to label these. So we got P, we got G, we got K0 as input, and then K3 in this case as the output pin. But before you actually assign the pins, it's always a good idea to click on the pin and make sure that the pin on the package, on the appearance, does connect to what you think is the P pins in this case. So it's always good to double check first, okay, and make sure that all the pins are the way they're supposed to be before you move the labels in and kind of document which one is which one. So we got P, G, K0, and then K3, like so. So we got one K circuit done. You guys have a question I can answer? No? Okay. All right, so now the question is, can I test the circuit just like the way it is? And the answer is absolutely. So this is the part where most people forgot how to use Logisim. It's just the same way as you place an AND gate or OR gate or exclusive OR gate or splitter into the circuit. When you are in the design where you need a component, you just click on the component that you need once, and then you put it on the other side. So this is basically you using a subroutine that you define in another subroutine that you're defining. Is that okay? So we'll just kind of slap it here somewhere, okay? And this is also where tunnels can come in handy. So let me show you why I think tunnels can come in really handy here. So I'm just going to be lazy by copy and pasting a little bit. So I'll duplicate P and G as tunnels and switch them to point the other side. And hook these up. So K0, we'll just kind of do the same thing here. So I might be, it seems like I'm doing something that may not be very useful, but all of this is to make it easier for the second K circuit that I need to do. Okay, and this is K3. K3 goes out to its own output pin anyway, so I can just attach a pin here. But before I do anything, I want to test it. In other words, I'm going to have to specify X, Y, and K0 so that I end up with a K3 being a 0 or 1. This is already one test case. What test case are we talking about? I can add 0 to 0 with an input of 0 as K0, and is it giving me the correct output? Is K3 supposed to be a 0 when I'm adding 0 to 0? Okay, that makes sense, right? The simplest case I can use here to generate a K3 to be a 1 is 100 plus 100. So I can say 100 plus 100 has an output of K3 being 1. Would that be correct? Okay? I cannot see how K0 can be useful here. Well, let's see how we can use K0 so that K0 actually matters, okay? Can someone give me a test case where K0 actually does matter? It is the determining factor whether K3 is a 1 or 0. Give me a test case like that. Yep. 1, 1, 1, and how about just a 0 for y, and then we can just vary K0. Okay, does that make sense? Okay, so we have 1, 1, 1 as x, 0, 0, 0 as y. So in this case, 1, 1, 1 plus 0, 0, 0 plus 0 is just 1, 1, 1, so K3 is a 0. We do not have an overall carry at all. Is that okay? What if I change this K0 to a 1? Then it becomes 1, 1, 1, which is 7, plus 0, 0, 0, which is 0, plus 1. 7 plus 1 is 8. And I cannot represent 8 using only 3 bits. So the carry output of K3 has to be a 1. Is that making any sense? So let's go ahead and test this. There we go. So I'm fairly convinced that the circuit is working, even though I only have like 3 test cases right now. You guys can generate other test cases as well. So you can put any one in here, okay? Any additional 1 in y or K0 should result in a K3 of 1. So it doesn't matter which one, okay? You can put a 1 here, you can put a 1 here, you can put a 1 here, you can put a 1 here. Is that okay? So I'm not only telling you what test cases you can use, even though your circuit is incomplete and relatively simple at this point, but you kind of have to think about why those test cases work. Okay? Why can't I just put a 1 anywhere within y or K0 to make K3 a 1? Okay? Why does it make sense? So you kind of have to think about that. Are we good so far? Yes? Okay? So all the heavy lifting is pretty much done. So from here on, it's easy peasy. So we go to project, add circuit. This time we're dealing with K2. So this is the K2 circuit, and I don't need K3 and K2. So we'll double click on K3 because I like to be as lazy as possible. So do a Control A, Control C, go to K2, slap everything back in. Then you go like, but that's not supposed to be K3. Okay, we'll change the circuit a little bit. It is not K3 anymore. Now it's K2. Okay, but it still doesn't make sense because K2 is a simpler circuit. Well, you're indeed correct because K2 is a simpler circuit. So the one G that is standing out by itself is G1. It's not G2. So let's fix that. So instead of G2 going into here, we have G1 going here. So we just remove that wire. We probably need to remove this one too. And then we just hook up G1 to the AND gate, to the OR gate. But then you will say the OR gate does not need 4 inputs anymore. It only needs 3. You're absolutely correct about that as well. So we'll change the number of inputs to the OR gate to just 3. And we can make it a narrow design like so. So that means, we have some rewiring to do, to make it look nice. But we'll deal with those later. So we just pick up this end, put it here. There we go. And we know the most complicated one doesn't need to be here anymore. Get rid of that. And we can leave the lines dangling. It doesn't look good, but it doesn't really affect the circuit either. So you guys can do the cleanup later. What about the one that has 2 input pins? It's P1 and G0. So we look at this one here, and we need to change that. Okay, P1, G0. So we need G0, which is this pin here, and then P1, which is this pin here. And of course, if you want to self-document, P1, G0 should be the new label. Are we good so far? Okay. But you can see why, it working the other way backwards, is easier, quote unquote, easier in a way, because I just have to remove components and rewire things a little bit, because I have everything that I need here already. I just need to kind of simplify it. Is that okay? And then we got the one left here, which is P1P. Oops, I'm looking at the right thing. P1P0K0. Okay. So the K needs to be cleaned up here. Now this is all really just for cosmetics, just so that it looks nicer. Yeah. Okay. So this one needs to be changed to P1P0K0. So we got most of the things we need already, except for the K0. So where it connects to G0, which is, this is another trick that you guys can use. If you use a poke tool and poke on the wire, it will highlight everywhere that it goes to. So this helps to identify which input pin I need to change in order to lose that connection to G0. Because I'm poking G0 here, this is bit 0 from G, so that tells me that the third pin of the 3-input AND gate is the one that I need to disconnect. So that's the one that we'll do. So we'll take out this connection here, and then we'll wire this up to K0. It's P1, P0, you're correct. Okay. So we get to keep P. So we need to take out this one too. And then wire up this guy. There we go. So time to use this in the main design and test it. Yep.
The label for the three input.
Oh, the labels are okay. You're right. Let's fix that too. Okay, there we go. Thank you. All right, but it's really ugly right now, but that's okay, because we can deal with ugly as long as it is still functionally correct. So we go back to the main design, we pull the K2 out, and you go like, oh, we need to rewire up everything. Copy, paste, and then a new wire. And we are done with that. Okay, so now we need to test K2, okay, which I did not label yet, but this is K2. So now we have to think about cases where K2 is going to be a 1 based on the input test case. So with this one, if I adjust the input where I put a 1 here, a 1 here, or a 1 here, they should all give me a K2 of a 1, okay? So let's check that. Yep, that works, and that works. Now, is this an exhaustive test to make sure that in every single test case it works? No, okay? But it's a reasonable test if you have a very short amount of time. It's a reasonable test to make sure that the circuit is in fact working. So are we good so far? Okay. All right, so I'm going to click on this design here. Since I did not label it, I should label it somewhere. So I'm going to label it over here. So I just say that this is my K2. At least I have some way to tell me what circuit it is. Is that okay? So now we only got K1 left. So we go to Project, add another circuit, call this one K1. And in order to do K1, we're going to copy and paste from this circuit, Control A, Control C, go to this K1 subcircuit, Control V, and we're almost done. So we switch back to the notes, and we look up K1. K1 is right here. Oh, that's really easy. G0 on its own to the OR gate. So the OR gate doesn't need 3 inputs anymore. It only needs 2. Okay, and you can see how this wire is actually not connected anymore. And we're going to lose this gate too because we don't need an AND gate with 3 inputs anymore. So we're going to lose that one, which also means this is gone. And this one hooks up to here. We are not going to connect G1 directly to the OR gate. And which one are we going to be connecting this time? It's G0. Okay, so we just hook it up to here. And then the AND gate is going to take K0 and P0. So we'll remove this wire and tap this one over here. And then this wire needs to go to P0, which means we'll remove this tap over here. Oh, okay, I'm going to just delete a whole bunch of stuff here. But you guys get the general idea. So we go here, change the design, so it's now P0, K0. And that's it. Okay, make sure that we have a appearance done, okay? And I'm not going to label these things because it's going to take up some time. So go back to main. This time we pull a K1 into this circuit. And just like last time, this is why I put all the tunnels over. Okay. Control D. Just have to be careful when I move them around. There we go. So now we have to test this bit here. This bit is only sensitive to bit 0. So when I exercise the pins, only the least significant bit would affect K1. So if I put a 1 here, K1 should be a 1. If I put a 1 here, K1 should be a 1 as well. But if all the other bits should not affect K1. Okay? So the test cases that I have used so far, you have to kind of understand why those test cases work. Okay, why I can test the circuit to a certain extent already, even though I do not have the sum bits yet. So are we good so far with this design? Okay. All right. So we got the K bits, and I'm going to label one more thing. I'm going to label the K1 chip, just so that it's easy for us to tell what it is. This is K1. All right. So we got K1, K2, and K3. It's time to calculate the sum bits. But what exactly are the sum bits? Well, we look up the notes again. Okay. The sum bits is defined to be the R, or the result after adding, between the Q and the K. What logic gate do we need in this case? Exclusive OR, okay? Because it's still an R function, so we need exclusive OR. So here's the tricky part. We are not going to bundle K1, K2, K3 into a single wire to use the multi-bit exclusive OR gate. Why not? Because bit 0 only relies on bit 0 of the other two, not bit 1 of the K. Let me point out again what I mean by that. Okay. So when you look at this equation, S1 depends on Q1, K1. S0 depends on K0 and Q0, not K1. And then S2 depends on Q2, K2. So K3 is not needed to calculate the sum at all. K3 is the actual output of a 3x3-bit carry look-ahead adder. It is not used to calculate the sum itself. So that means this part of the circuit, we'll just kind of move it down here. And then we'll just reposition things a little bit so that it's easier to do the merger, which is basically a splitter. You just look at it in reverse. Okay, so we need K0 to be one of the bits here. And put it here. There we go. And then we'll take a splitter and merge these three into one. So we go to wiring, and then we use a splitter, except we change the phasing. So now it is a merger. So what is the difference between a splitter and a merger? Which side it's facing. They're basically the same thing. Is that okay? So these are all 3-bit items, and we also need 3 split ends. So let me just kind of explain the split end concept one more time. When you look at the properties of a splitter, phasing is really just which end the split end is facing. Okay, so if it's west, that means the split end is facing west. If it's east, it means the split end is facing east. So the phasing only has to basically is controlling which side is the split end. Fan out says how many connections do we have on the split end. You can have up to, and including the bit width as the number of split ends. But you don't have to. So if you only need 1 bit out of 3, you can make fan out 1 and only extract that 1 single bit. Okay? Bit width basically says the entire bundle of wires. How many bits are we containing? So that has to be 3 in this case. And then bit 0, bit 1, bit 2, all of these are controlling which wire of the split end corresponds to which bit of the entire bundle. If you want your wiring diagram to look really difficult to understand, you can do something like this. Bit 0 connects to the middle, bit 1 connects to the top, and then bit 2 connects. Oh, no, this is still too easy. Let's make it more difficult. Let's make this one go to 0, and this one go to bit 2. Now you have a splitter that makes no sense, but you can still make it work. Do you see how the bits are now kind of like all over the place? It'll still work if you are very careful connecting the wires. Why would you do something like that? Probably no particular reason other than just showing that you can, okay? So I'm going to do it like this, just the way it is, okay? So, but the important part is we just need to connect bit 0 to bit 0. Wherever it is in the splitter, that's where we need to connect it to. So K0 now connects to bit 0, which is now the middle wire. Bit 1 connects to the top wire. Oops, nope, the bottom wire, because that's where it says 1. And then bit 2 connects to the top, because that's where it's labeled 2. It'll still work. So have I sufficiently explained how a splitter works and how you can control the positioning of each individual bit on the split end? What if you want this is not one of those cases where you can combine different bits into one wire, even on the split end, but there are cases where you can do that. But I'm not going to demonstrate it because it's not needed here. So I got all the cases combined. I just need another exclusive OR gate here. So we go to gates. Oh, we got one already. Might as well just borrow that. Okay, so we got one exclusive OR gate. So we can hook up this wire directly to here. And then the other one is coming from where? Q. Very good. So we got Q as a tunnel over here. Or if you're really sick and tired of using tunnels, you can just do it here too as well. That works. Is that okay? And then the output is the sum bits, which is an output pin. And I'm going to label this S here. It needs to be 3-bit wide and needs to be connected like that. So now we got almost the entire thing done except for K3. Also needs its own output pin like so. And I'll label that K3. So it's time to test it again. So give me a test case. We got to test this one. Let's not use these kind of trivial test cases. Does someone want to test it? Yep, go ahead. 111 plus 111. Okay. So before you test the design, before I enter the other 111, what should be the output? No. 111 plus 111 is not 000. It's 110 with an overall carry of 1. Okay, so 111 plus 111 has K3 being a 1, and then the sum itself being 110. Okay, well, let's double check. Does that make sense? 111 is 7, right? 7 plus 7 is 14. I cannot represent 14 using only 3 bits, because 3 bits can only give me up to 7. Does it make sense? So that means I'm going to have an overall carry of 1. But that so-called carry of 1 is 1 of what? 1 of 2 to the power of 3, which is 8. So I have a value of 14 to represent. The carry alone is representing 8 of the 14. How much is left for the sum bits to represent? 6, which is 110. So that's the other way to look at the output of this particular calculation. Yep.
I have just a question about that last gate, which is XOR gate.
Uh-huh.
Why instead of that XOR gate we don't have AND gate? Because Q and K makes sound, not X.
Q exclusive OR K makes the sum bit. Not AND.
You do not have to add both of them to get the sound. You do not have to add Q and K to get the S.
Okay, so let's check our equation again. This is how we conclude at this point that the sum bit is applying the R bit or the R function to Q and K. But the R function is exclusive OR, so we are basically using exclusive OR as a gate to compute all the sum bits. There's no AND in it. The AND is only needed for carries, but not for the sum bit. Okay?
Where does it say that R is exclusive OR in the formula?
It's down in section 5. So in section 5, we are trying to use logical operations to replace the arithmetic operations. So right here, this says, the other one is a little harder, blah, 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 blah.
The one on the bottom here.
Yeah. So it first explains, we have one single exclusive OR operator that can do this. But if exclusive OR is not available, because it is not one of the logical operators defined in C and C++, then we can use the longhand of expression like this. You can see how I hide a lot of, things in my notes. It's not. I'm doing a very good job. Okay, so that means you guys need to buy highlighters to help you, right? Highlighters and write your own notes. Okay, that can be helpful as well. All right, so let's go ahead and test this. Okay, we were talking about the test case. 111 plus 111 is 1 as an overall carry, and 110 as the sum. So that works. But I'm here to explain, in addition of, why this is in addition that this is the answer, why it is the answer, from the perspective of 7 plus 7 is 14. We still get the 14 back from adding 7 to 7. It is just represented a little bit strange because we have a carry which is representing an 8, but then the rest of the bits is representing 6. 8 plus 6 is still 14. So are we good so far? Yes? And let me just look up the time here. Oh, it's only 42. We got 8 minutes left. What do you say if I turn this into a subtractor or an adder / subtractor? It can do both. Yes? Okay. So what is the difference between an adder and a subtractor? Okay. It's the way we define P and G. Okay, very good. What is the difference between the definition of P and G for an adder as opposed to the P and G for a subtractor? Do you guys remember? One has X negated. Okay, for a subtractor, X is negated before the and, X is also negated before the or to come up with the P and the G terms, or G and the P terms respectively. Okay, so otherwise the circuits are exactly the same. Is that okay? So the first thing we're going to do here is to say, okay, so how do we add a negation to X, in this circuit? Let's check this out. So you click on one of the gates. This one doesn't apply because it's a Q, but this one does, okay? Because we are here to calculate P. Do you see these two over here? You can negate an individual input. So you can negate the first input. You can also negate the second input, which comes in very handy for what we are doing. So over here, we're going to do this part here and say, let's go ahead. Okay, let me extend this so you can see see the entire thing. So we can negate a particular input pin before it gets into the gate itself. You can add an external gate if you want to, okay, which we'll end up doing, okay, but I just want to test it first. Because if TAC is saying that it is a very simple thing to do, okay, is it really that simple? Is it really just negating X, then we have a subtractor? That's the question. Well, what do you see here? Do we see a subtractor at work? Okay, let me see if I can show you the whole screen again by shrinking this portion. Well, now we have 111 minus 111. Do we get 0 with no borrow? Does that make sense to you? Seems to make sense. How about 111 minus 111, but with K0, which is now T0, okay, the first borrow, the 0th borrow bit as a 1. What should we get? Which boils down to 111 minus 111 minus 1. What should you get? You should get a result of 111 with an overall borrow of 1. Okay? Because 111 is 7, minus 111, which is also 7, is 0. But 0 minus 1 is negative 1. But what is how do we represent negative 1? We're not going to do that, right? We'll say there's an overall borrow of 8, but a result of 7. So you got $7 in your pocket, but you owe the bank $8. So your net worth is negative 1. Is that okay? So let's check it out. We just have to flip one bit to test that, right? Ta-da! So now you owe the bank $8, but you have $1, $2, $4, $8 in your pocket. We got our subtractor. Well, if the subtractor is really that little of a change compared to an adder, can we combine a subtractor and an adder into the same circuit and have one input pin to say, I want this to be an adder now, I want this to be a subtractor now? What do you think? Should be doable, right? So I'm not asking you to do this as a homework assignment, but once I'm done with this, you should understand how it works, okay? So we'll have one input pin, one extra input pin here oops, that's an output pin. So we have one extra input pin here, and I will say that this is a subtractor / adder. So the way I specify it means if it's a 1, it's a subtractor. If it's a 0, it is an adder, okay? And this is what I'll do next. I'll do something that seems to be kind of silly, okay, because I'm going to use a merger like this one. I only got one bit. I'm going to use a merger. Doesn't seem to make sense. It seems to be hooking up the wires, all wrong. In fact, I'm going to do something like this. This looks so wrong, right? I have one single bit, now it's 3-bit. I'm replicating 1 bit into 3 and then putting it into one bundle of 3. That definitely seems wrong. If it seems right to you, there's something wrong. So I'm going to take this and move it around a little bit here. Take this out. Take this out. And I'll also take out the built-in negation of the gate. I'll take those out. Okay. And then I'll take X here. And I'll put a gate in here. Whatever gate I put in there is going to feed into these wires. So I'm just going to give you an idea of where the wires are going to, and then we'll figure out what gate needs to go in between. Okay, so right here we have a gate that needs 2 inputs and 1 output. And it is a combination of SA, which is subtractor / adder, and the original X pin. We know the width is compatible because X has 3 bits, right? X is 3-bit wide, but so is this. So now we just need to figure out a gate where if it is a 1 coming from SA, it is negating. If it is a 0, it is not negating. And what gate do you think can do this trick? Nope, it's not an AND. It's this guy. It's exclusive OR. So I wire this up, and now the circuit should be working. Since it is S/A, which means, the slash means if it is a 0, it's doing it the adder. If it's 1, it's doing a subtractor. So right now it's acting as an adder. Is it acting like an adder?
Yes.
111 is 7 plus 111, which is 7, is 14. 14 plus that last one is 15. 15 is 8 plus 7. That works.
It gets exactly the same result.
Huh?
That is a subtractor.
If it's a subtractor, does it work out the same way? Let's figure out. It does work out the same way, because if it's it does, okay, well, we'll pick another test case, right? Okay, let's find another test case then. What about the easy ones, right? It means 0, 0, 0, and then 0, 0, 1 with no overall stuff, okay? Does that work now? This is 0 minus 1. 0 minus 1 is 7, but we owe the bank $8. That works, right? Let's turn it into an adder. Does it work? It works. So what kind of trickery, what kind of black magic is involved here? Why do you think a single exclusive OR can do this? Okay, so I need to explain this part before we end the class because this is kind of the important part, right? Okay, except my notepad is, oh, there we go. Okay, so we have x, we have, okay, this is not x, this is x again, and this is the pin that we call subtractor slash adder, right? Okay, so we have 0, 0, 0, 1, 1, 0, 1, 1. So you just have to kind of figure out, what is the output coming out of the exclusive OR. So X exclusive OR SA, we got a 0 exclusive OR 0 is what? 0 exclusive OR 1 is 1. 1 exclusive OR 1, 1 exclusive OR with 0 is a 1. 1 exclusive OR with 1 is a 1. So now you look at, sometimes we just need the negation of x. The negation of x is 1, 1, and then a 0, and then a 0. Do you see how it works? How these two in the middle is working? It's actually, I take it back, because these two, okay, if you look at this row, and you look at this row, they are both corresponding to when the SA pin is a 1. So when the SA pin is a 1, then we get a negation of x. Is that okay? What if I want to get x back? Okay, so this is 0, 0, 1, 1. So you look at the first and the third row. Look at the first row, we get x back. The exclusive OR between the pin is the same thing as x. When you look at the third row, it is also the same case. So that's how the exclusive OR gate can help us control whether we want to do a bitwise NOT or not. Yes?
So, the last row,
Mm-hmm.
the third column be a 0 because it's an excellent instead of an OR?
Which one?
Oh, on the very bottom.
Oh, this one? Yeah, I got a mistake here. There we go. Yep. But that's why we can use an exclusive OR gate to do this. Now, do I expect you guys to come up with a design like this, that can, kind of integrate or unite an adder and a subtractor? Not without explanation, okay? If I explain this kind of logic first, you should be able to put it together. But now that it's together, now that I have put it together, do I expect you to understand that it works? Yes. Because it relies on only the understanding of a 3x3 carry log ahead adder, carry log ahead subtractor, and how exclusive OR works. So given the design, given what you should understand at this point about all of these components, I do expect you to understand how this overall design to work as both an adder and a subtractor, depending on how this particular input pin, whether it's a 1 or a 0. Okay, so I'm going to save it, and I will post it on Canvas so that you guys can download it and study if you want to. And for those of you who absolutely cannot handle the way I wire up things, you can make it pretty again. I don't like to make things pretty. I just make it work, and then I move on. All right, I'll see some of you at the first lab, and then there'll be the second lab as